Hello dear students, welcome to the ACE online platform. I am Malakondaya Gandham, thermal faculty in our academy, having more than 25 years of experience in teaching. Okay, in this platform we are going to discuss the solutions for NAT type of questions, means numerical answer type questions, and MSQ questions, means questions which are having more than one option correct. Okay, and this series we named as score boosting series. Okay, we are divided the thermal part into two parts. One is basic thermodynamics and the second part is applied thermodynamics. Today we will take the basic thermodynamic questions, and 30th of this month, 30th of December, we will take the questions from the applied part of the thermodynamics. Okay, first let us take the NAT type of questions. Look at the very first question, right? Look at this question. Try to read the question clearly to understand what it is given and what you are asked to find. Given like this: a reversible cycle receives 40 kilojoules of heat from one heat source at a temperature of 127 degrees centigrade and 37 kilojoules of heat from another heat source at 97 degrees centigrade. The heat rejected in kilojoules to the heat sink at 47 degrees centigrade is how much? Indirectly you are asked to decide what is the magnitude of the heat rejection, which is in kilojoules. Okay. Now look at the question. It is given for reversible heat engine cycle. Okay, the schematic diagram or the arrangement of the cycle may be like this. Let this is the one source which is maintaining 127 degrees centigrade, 127 degrees centigrade, and another source, this is another source maintaining 97 degrees centigrade. These two sources are for supplying the heat transfer to the reversible heat engine from the source maintaining T1 temperature is Q1. Assume this is the T2, source 2 temperature is T2, is giving the heat energy for reversible heat engine a magnitude Q2. These two are for supplying the heat, and it is rejecting the heat to the sink. That sink temperature is given 47 degrees centigrade. 47 degrees centigrade. Assume the sink temperature is T3 for receiving the Q3 amount of the heat energy. Okay, this Q3 is how much? Q1 given as 40 kilojoules. This Q1 is equal to 40 kilojoules, and Q2 given the heat available for the reversible heat engine at 97 degrees centigrade is 37 kilojoules. 37 kilojoules. Q3 is how much? For that you have to take the temperatures in Kelvin only. T1 equal to 127 plus 273, T2 equal to 97 plus 273, T3 equal to 47 plus 273. All are in Kelvin. Okay. Then according to Clausius inequality equation, Clausius inequality equation is cyclic integral del q by t always less than or equal to 0. This is the Clausius inequality equation. The cyclic integral del q by t equal to 0 for a reversible cycle. For a reversible cycle, cyclic integral del q by t is less than 0 for irreversible cycle. Irreversible cycle. And one more condition also I can write: cyclic integral del q by t greater than 0 is impossible. Impossible. Okay, but it is clearly given that the heat engine is working by a reversible cycle. For a reversible cycle, this is the condition. By using this condition, you can decide the amount of heat rejected to the sink. Okay, here cyclic integral del q by t 0 means q1 by t1 plus q2 by t2 minus q3 by t3 must be equal to 0. The reason why we have written minus q3 is, q1 and q2 are the heats entering to the heat engine. Thermodynamically, heat entering to the system is taken as positive, but the q3 amount of heat is leaving from the system. Thermodynamic sense for heat transfer is such that heat leaving from the system should be taken as negative. For that we have taken q1 by t1 plus q2 by t2 minus q3 by t3 equal to 0. It can be also written as q1 by t1 plus q2 by t2 equal to q3 by t3. Q3 by t3, or q3, the amount of heat rejection q3 equal to, right, t3 into q1 by t1 plus q2 by t2. T3, look at the T3 value. T3 47 plus 273. 47 plus 273 into q1. Look at the q1. q1 is 40 divided by 127 plus 273 plus q2. Look at the q2 is 37 divided by 97. 37 divided by 97 plus 273. So here T2 T1 127 yes. You simplify this value, operate your calculator for getting the answer. My calculator has shown 64 kilojoules. 64 kilojoules. That is the answer. So answer is, since it is asking in kilojoules, 64, that's all. That is the answer. It is the one of the numerical, right, answer type question. Generally for this kind of questions, range will be given. Look at the range for this problem, 63.5 to 64.5. We got 64. Our answer is absolutely correct. I hope all of you clearly understood. Understood or not? Yes. Then let us take the another question, another NAT question. It is asking like this: in the vicinity of the triple point, you know the meaning of triple point, the point where the solid phase, liquid phase and gaseous phase of the same working substance can be existing under equilibrium state. Thermodynamic equilibrium state is called triple point state. Okay. So in the vicinity of the triple point, the equation of the liquid vapor boundary in the PT phase diagram for ammonia is ln P equal to ln P equal to 24.38 minus, let me 1 minute, right, otherwise let us take a 1 minute. Here ln P equal to ln P equal to 24.38. Should be very careful while we are discussing in the limited space, minus 3063 divided by absolute temperature T, where P is the pressure in kilopascal and T is the temperature in Kelvin. That is for liquid phase vapor boundary. Next, similarly, the solid phase boundary is given by these for liquid vapor phase boundary. Next, another condition is given for solid vapor boundary. For the solid vapor boundary, the ln P equal to 27.92 minus 3745 by T, 3745 divided by T. Okay. The temperature at the triple point in Kelvin is, you are asked to decide the temperature which is in Kelvin. Now, triple point, let me briefly explain the meaning of triple point. Triple point meaning is like this: you take the water in a container, you take some water in a container, up to certain level, means above the water level some atmospheric air is there. Initially, the pressure which is acting on the surface of the water by the atmospheric air is roughly 1 bar. For maintaining the low pressure on the surface of the water, what I am doing is, I am connecting a vacuum pump. I am connecting a vacuum pump for the vessel. This vacuum pump can lift the air from the surface of the water. This is the air lifting process. Once the air is lifting from the surface of the water, the pressure which is acting on the surface of the water keep on reducing. Once the pressure on the surface of the water reaches to 0.00611 bar, at this pressure a part of the water is becoming ice, that is solid. A part of the water is becoming steam, that is vapor. The remaining part of the water is available as in liquid state. So, at this pressure, water can be available as ice, that is solid, as steam, that is vapor, and liquid water. Though the solid state, vapor state and liquid state are existing at this particular pressure, these three are maintaining the same temperature, that is 0.01 degrees centigrade. This particular temperature we are calling as triple point temperature, and the corresponding pressure triple point pressure. Since the three phases are maintaining the same temperature, the system is under thermal equilibrium, and three phases are maintaining the same pressure. Equality of pressure means mechanical equilibrium, and there is no chemical reaction between these three phases. Therefore, the system is under chemical equilibrium. As you know, if any system is maintaining chemical equilibrium, thermal equilibrium and mechanical equilibrium, that kind of system is said to be under thermodynamic equilibrium state. From that you can conclude that the thermodynamic equilibrium state is the triple point state is the best example for thermodynamic equilibrium state. Now that triple point state in PT diagram, pressure versus temperature diagram, I can mark like this. Let me mark the pressure for water only. This is the triple point pressure for water. 0.00611 bar, pressure is in bar, and temperature which is in degree centigrade. That temperature is how much? 0.1 degree centigrade. This is the 0.01 degree centigrade. You project a vertical line from temperature, horizontal line from pressure. Wherever these two are meeting, that is the representation of triple point state. At the triple point state, liquid phase, vapor phase and solid phase are maintaining same pressure. That means the conclusion is LNP for solid phase must be equal to LNP for the vapor phase must be equal to LNP for liquid state. Okay. Since the LNP is given for liquid and this is for solid, that means whatever the LNP given for liquid vapor region or liquid vapor phase, that must be equal to LNP for the solid vapor phase. Okay. That means indirectly these two quantities are equal. Once the left hand side values are equal, you can equate the right hand side values. Then let us equate the right side values 24.38. So let us take 24.38 minus 3063 by T, 3063 by absolute temperature must be equal to 27.92 minus 3745 by T, 3745 by T, 3745 by T. You simplify this value, operate your calculator for getting the answer. From this T value, my calculator has shown 195.2 Kelvin. That is absolute temperature. So 195.2, answer is 195.2. That is the answer. Okay. Let us see the range which is given. Look at the range, 194.5 to 195.8, but our answer is 195.2. Since this value within the range, our answer is absolutely correct. Understood clearly? Easy only, but quite lengthy problem. Okay. Let us take the another question. Look at this one. It is asking like this: ambient air is at a pressure of 100 kilopascal, means barometric pressure. Barometric pressure is 100 kilopascal. Dry bulb temperature of 30 degrees centigrade. Dry bulb temperature of atmospheric air given 30 degrees centigrade. And 60% relative humidity, RH value given. Relative humidity RH equal to 0.6. The saturation pressure of water vapor at 30 degrees centigrade is 4.24. That means corresponding to this dry bulb temperature, the saturation pressure given 4.24 kilopascal. Okay. The specific humidity of the air in grams per kg of dry air, you are asked to decide specific humidity of the air in grams of the water vapor per kg of the dry air, correct it to 2 decimal places. Okay, that is the question. For that, let us take the relative humidity formula first. RH value equal to ratio between the partial pressure of water vapor and partial pressure of the saturated water vapor. From this I can write that partial pressure of the water vapor equal to RH times the partial pressure of the saturated water vapor. RH value 0.6 given, partial pressure of the saturated water vapor 4.24. That is the partial pressure of water vapor. Then what is the specific humidity? Specific humidity equal to 0.622 into PV by PB minus PV. Right? It is equal to 0.622 into PV value. PV equal to 0.6 into 4.24 dividing by barometric pressure given 100 kilopascal. If not given in the question, you can take a standard atmosphere pressure is roughly 1 bar, that is equal to 100 kilopascal or 101.3 kilopascal, that is the exact value. Barometric pressure 100 minus PV 0.6 into 4.24. You simplify this value for getting the specific humidity, right? Specific humidity, right? Right. So I directly found in grams per, since it is asking grams per kg of air. From this formula you are getting in kg of water vapor per kg of the dry air, right? From this formula we are getting some value which is in kg of water vapor per kg of dry air. Let us say that is X. But answer is asking in grams per kg of the dry air. That's why you multiply this X with 1000, because 1 kg equal to 1000 grams. 1 kilogram equal to 1000 grams. That's why multiplied with 1000. You will get the required answer. My calculator has shown 16.23 grams per, that means grams of the water vapor, grams of water vapor per kg of the dry air. Psychrometric properties are generally decided in terms of kg of dry air only. 16.23, that is the answer. 16.23, right? 16.23, that is the answer, right? Since it is asking to correct for 2 decimals, I have taken only 2 decimals, 16.23. Look at the range, 16 to 17, right? Our answer is 16.23. Okay, that is how the NAT type questions are asking in the exam. Okay, the next part of questions are the questions which are maintaining options more than 1 correct. They are called as MSQ questions. Okay, now let us take the MSQ type of questions. Look at the very first question, right? Look at this one. It is asking like this: which of the following statements is /R are correct? First option, look at the first option. If the isentropic process is irreversible, it must be non-adiabatic. Absolutely correct. As you know, change in entropy ds equal to del Q by T plus entropy generation. This entropy generation always greater than or equal to 0. Okay, this entropy generation is equal to 0 for any reversible process. For any reversible process. S generation greater than 0 for irreversible process, for any irreversible process. Remember, entropy generation less than 0 is impossible. Entropy generation less than 0 is impossible. Okay? Since the option is asking if the isentropic process is irreversible. Isentropic process is irreversible means this entropy generation, this is more than 0. More than 0. Let us take some value, some numerical value for your understanding. Since it is irreversible process, let us take S generation is equal to, let it be 2 kilojoules per Kelvin. Right. The second part is 2 kilojoules per Kelvin. For isentropic process, ds must be equal to 0. For isentropic process, ds must be equal to 0. For having the ds 0, with S generation is positive, the del q by T must be equal to magnitude wise equal to 2, but that must be negative. Therefore, this del q by T must be minus 2 kilojoules per Kelvin. Then only this entropy change can become 0. That kind of process you are calling as isentropic process. So, from this the moral is, if the isentropic process is, here ds0 means what? ds0 means it is equal to S2 minus S1. S2 equal to S1. That means entropy remains constant. Isentropic process. Entropy constant means isentropic process. So, if the isentropic process is irreversible, that must be non-adiabatic. Non-adiabatic means heat transfer must be existing. Adiabatic means heat transfer 0. Remember, if the isentropic process is reversible, if this fellow is 0, for having the ds 0, del q by T must be equal to 0. For that, if the isentropic process is reversible, that must be sorry. If the isentropic process is reversible, that must be adiabatic. But if the isentropic process is irreversible, that must be non-adiabatic. That means reversible and adiabatic condition. Reversible plus adiabatic condition. This condition may maintain constant entropy. Otherwise, irreversible, non-adiabatic. Irreversible, non-adiabatic. This another condition may maintain constant entropy. Okay? That means if the isentropic process is irreversible, that must be non-adiabatic. If the isentropic process is reversible, that must be adiabatic. Okay? Look at the option A. If the isentropic process is irreversible, it must be non-adiabatic. It is absolutely correct. It is MSQ question. MSQ question is having more than one options correct. Look at the B. A Gibbs function remains constant in the phase change process for a pure substance. That is also correct. That is also correct. Gibbs function, as you know, Gibbs function G equal to H minus Ts. H minus Ts. Okay. Then dg equal to dh minus Tds minus SDT. Minus SDT. But what is the H value? As you know, H equal to what? H equal to U plus PV. Na? H equal to U plus PV. Then dH equal to du plus PdV plus VdP. dH equal to du plus PdV equivalent to del Q plus VdP. It is asking for phase change process. Phase change process for a pure substance. phase change process like vaporization, freezing, melting, fusion, these are all the phase change process. All the phase change process are treated as reversible process. For any reversible process, del Q equal to TdS. Del Q equal to TdS for a reversible process. Because for a reversible process entropy generation equal to 0. Okay? Because you know ds equal to what? ds equal to del Q by T plus entropy generation. For a reversible process, this fellow is becoming 0. Then del Q equal to TdS. So in the place of this del Q, dH equal to TdS plus Vd. TdS plus Vd. That is the dH value. Let us write that value here. dG equal to dH. Look at the dH. TdS plus VdP. TdS plus VdP minus TdS minus SdT. Okay, here plus TdS minus TdS cancelled. Finally, dG, change in Gibbs function equal to VdP minus SdT. That is the change in Gibbs function. Okay. Now, it is asking for phase change process for any pure substance. You know, all pure substances can maintain the phase change process or can have the phase change process at constant temperature and constant pressure. That means for any pure substance, during the phase change process like evaporation, that is vaporization process, not only temperature constant but also pressure remains constant. For any pure substance, in the phase change process, like vaporization process, pressure is remaining constant, temperature also remaining constant. You take the water. While the water is evaporating at atmospheric pressure, from the beginning of the evaporation to ending of the evaporation, it is maintaining constant temperature, that is 100 degrees centigrade. You might have drawn the graph like this. If you look at the temperature versus entropy coordinate system for a pure substance, the saturation dome is appearing like this. This is the saturation dome. The apex point is representing the critical point. Then one of the constant pressure line. This is one of the constant pressure line. A be the beginning of the vaporization, B be the ending of the vaporization. So A to B be the phase change process called vaporization. In this vaporization process, pressure is constant. Look at the temperature also remaining constant. That means for all pure substances during the phase change process, both pressure and temperature remaining constant. If pressure is constant, what about the dP? 0. Similarly, since temperature is constant, dt equal to 0. That means for the phase change process, for any pure substance, dt equal to 0, dP equal to 0. Then what is the dG? dG equal to 0 minus 0 equal to 0. That means change in Gibbs function remains 0. It is written as G2 minus G1 equal to 0 or G2 equal to G1. That means Gibbs function remains constant during the phase change process for any pure substance. That means Gibbs function at state A equal to Gibbs function at state A equal to Gibbs function at state B, right? So anyhow, right, Gibbs function remains constant during the phase change process for any pure substance, absolutely correct. So A is correct, B also correct. Look at the option C. The boundary work is non-zero for a system maintains rigid boundary. The boundary work is non-zero for a system maintains rigid boundary. Correct. Because what is the boundary work? Boundary work means displacement work, right? Boundary work is displacement work. Okay. Boundary work is displacement work. Here displacement work equal to what? Displacement work means non-flow work. Displacement work equal to PdV. Displacement work is PdV. The boundary work is non-zero. No, boundary work is non-zero. For the system maintains rigid boundary. Rigid boundary means no change in volume. You take the water tank connected to your house. The water tank is maintaining rigid boundary. Therefore, there is no change in volume. There is no change in volume of the system. The change in volume is 0, right? Then what is the displacement work? 0. Displacement work 0. But what it is given? The boundary work is non-zero. For the system maintains rigid boundary. No. The boundary work must be 0 for the system maintains the rigid boundary. C not correct. C is absolutely wrong. Right. Next, D. First law gives the concept of direction of energy transfer. No. Second law of thermodynamics gives the concept of direction of energy transfer and entropy. First law simply speaks about the conservation of energy. According to first law of thermodynamics, energy cannot be created, cannot be destroyed, but one kind of energy can be converted to other kind of energy. Anyhow, D is absolutely wrong. D is absolutely wrong. Only A and B are correct. Means A and B, more than one option is correct. Understood? That is how you need to decide, right? Options, required options for the MSQ type questions. Okay, you should be very careful while you are reading the statements given for MSQ type questions particularly. I hope all of you clearly following or not? Yes. Then look at the next question. Look at the next one. Look at this one. Look at this one. Which of the following statements is / are correct? Look at the statement A. SFEE, popular equation called steady flow energy equation. Steady flow energy equation is applicable for only reversible process. Absolutely wrong. Steady flow energy equation, let me write the steady flow energy equation per kg of the material, GZ1 plus C1 square by 2 plus H1 plus Q is equal to GZ2 plus C2 square by 2 plus H2 plus work interaction. This is the steady flow energy equation for 1 kg mass of material. C1 and C2 are the velocities. This is the steady flow energy equation applicable for, it is applicable for both reversible process and irreversible process. Remember that point. The steady flow energy equation is valid for both reversible and irreversible process. Now, steady flow energy equation is applicable for only reversible. Absolutely wrong. Okay. Similarly, there is a non-flow energy equation, Q equal to W plus du. This is the energy balance equation for a closed system. This you are calling as non-flow energy equation. This non-flow energy equation also applicable for both reversible and irreversible process. Important point. Both steady flow energy equation and non-flow energy equation both are valid for both reversible process and irreversible process. That's why we took option A is absolutely wrong. A is wrong. Next, look at the B. Q equal to PdV plus du is applicable for only reversible process. Absolutely correct. Because you know Q equal W plus du, this is a non-flow energy equation valid for both reversible and irreversible process. But you know work equal to PdV, it is for only for reversible process. Only for reversible process. Okay. Then it can be modified as, in the place of W, let me write the P dV plus du. This equation is valid for only, this is the equation for only reversible process, because W equal to P dV, this W equal to P dV only for a reversible process. Anyhow, this is valid for both reversible process and irreversible process, whereas this equation is valid for only reversible process, right? Therefore, option B absolutely correct. Q equal to P dV plus du is applicable for only reversible process, correct. Look at the C. Cyclic integral del Q by T equal to 0 for simple vapor compression refrigeration cycle. No. Option C is wrong. Cyclic integral del Q by T equal to 0 for a reversible cycle. This symbol is for only reversible cycle. Okay. But given vapor compression refrigeration cycle, if you look at the vapor compression refrigeration cycle, it consists of one process irreversible, that is throttling process. Vapor compression refrigeration system consists of a compressor. This compressor may be operating reversibly, condenser working reversibly, throttling device is for dropping the pressure by friction. Capillary tube which is connected to our domestic refrigerator is working by throttling process. In the throttling process, pressure is dropping by friction. Since friction is causing for dropping the pressure in the throttling device, the process connected to throttling device is coming under irreversible process, right? If any cycle is maintaining all reversible process, that kind of cycle is called reversible cycle. Example, Otto cycle, Carnot cycle, Rankine cycle, Brayton cycle, Atkinson cycle. These are all the cycles which are constructed to work with all reversible process. Whereas this fellow, another device is evaporator. This fellow is working with three reversible process. Let me write it. This is the condenser, evaporator. The process with compressor, condenser and evaporator reversible. But the process with the throttling device is irreversible. Since one of the process for vapor compression refrigeration cycle is irreversible, therefore vapor compression refrigeration cycle is coming under irreversible cycle. For irreversible cycle, cyclic integral del Q by T not equal to 0 means less than 0. Let me complete the cycle first, right? Let me complete it. This is the compressor. You know, vapor which is coming out from the evaporator is entering to compressor. Because of the compression, pressure increases, then it is entering to condenser where the heat is rejecting. Then the vapor is becoming liquid. This liquid is entering to the throttling device, right? So because of the throttling is happening at constant enthalpy. Because of throttling, pressure and temperature both are decreasing. Then the liquid at a low pressure and low temperature is entering to evaporator for extracting the heat from working stuff, whatever you placed in the evaporator. So this is the vapor compression refrigeration cycle. Now if you look at the different states, 1 to 2, generally it is reversible compression called isentropic compression. 2 to 3, constant pressure condensation. 2 to 3, constant pressure condensation. 3 to 4, throttling process. 4 to 1, evaporation. So this is the reversible process. Process with compressor is a reversible process. Process with condenser is a reversible process. Process with evaporator is a reversible process. But process with the throttling device is irreversible process. That means one of the process in vapor compression refrigeration system or cycle is irreversible. Therefore, VCR cycle, vapor compression refrigeration cycle, VCR cycle is irreversible cycle. For irreversible cycle, cyclic integral del Q by T less than 0, according to class is unequal, less than 0. For vapor compression reference cycle, cyclic into del Q by T less than 0, but what it is given? Equal to 0, absolutely wrong, C is wrong. Look at the D. Entropy change is negligible, negative, entropy change is negative for system in the isothermal compression process, absolutely correct, absolutely correct. Entropy change is negative for the system in isothermal compression process specifically, you know, right. Right. Now, let us take the compression process. In the compression process, pressure increases. In the compression process, pressure increases. Along with pressure, temperature is supposed to be increased. The general nature of the gas is that during the compression process, along with the pressure, temperature increases. But you want to compress the gas isothermally, means constant temperature. To maintain the constant temperature during the compression process, though the pressure is increasing, counter effect is required. That is, right, cold source. Once we add the cold source, while the gas is compressing, for that cold source, the compressing gas is dumping the heat. Because of the dumping the heat, the gas temperature decreases. The combined effect of gain in temperature due to gain in pressure by compression and drop of temperature due to cold source, that combined effect may maintain the constant temperature. That means, to have the constant temperature during the compression process, cold source must be required. For that cold source, gas is rejecting the heat. It is like this. If you take the bicycle pump mechanism, if you take the bicycle pump, let us take the bicycle pump. Let this is the bicycle pump. This is the piston inside the cylinder. Inside cylinder. This is your gas. I am placing this bicycle pump in a bucket of cold water. This is a bucket of cold water. Cold water bucket. When by the time I am pushing down the piston, what is happening? Gas is compressing. During the compression process, pressure increases. Along with the pressure, temperature increases. That high temperature gas which is inside the cylinder can dump the heat to the surrounding cold water. That means the gas is rejecting the heat to the cold source. Here cold source is, right, receiving the heat energy from the gas. Here the gas present in the cylinder is our system. That gas is rejecting the heat to the cold source, then the temperature of the gas decreases. Then the combined effect of gain in temperature due to compression and drop of temperature due to cold source may maintain the constant temperature. That means cold source is the counter effect for having the isothermal compression. Similarly, hot source is the counter effect for having the isothermal expansion. Anyhow, for compressing the gas isothermally, heat must be rejected. Heat must be rejected means this heat should be taken as negative heat, because thermodynamically heat rejection is taken as negative. Then what is the change in entropy? Change in entropy ds equal del Q by T. Del Q by T. In the isothermal compression process, this del Q is negative. Since del Q is negative for isothermal compression, the change in entropy is negative. Change in entropy negative means entropy decreases. Entropy decreases during the isothermal compression. That's why we have taken option D correct. Let us read the option D once again. Entropy change is negative. Entropy change is negative for system. System means gas in the isothermal compression. Absolutely correct. So here B and D, option B and D are absolutely correct. A and C are wrong. Okay. Following clearly? Let me have water. 1 minute. I'll get back to you. Right. Similarly, let us take the another question. Look at this one. It is also the question maintaining the options more than one. Which of the following statements is/are are correct? Let me read the option A. Steady flow reversible adiabatic work is equal to change in enthalpy with negligible velocity change and elevation change. Absolutely correct. Steady flow reversible adiabatic work is equal to change in enthalpy with negligible change in velocity and change in elevation. You know, with negligible change in velocity and change in elevation, relation between the steady flow work and non-flow work is steady flow work equal to sum of the non-flow work and P1 V1 minus P2 V2. That is the relation between the steady flow work and non-flow work for any process. But our option is given for reverse adiabatic process. This non-flow work for a reversible adiabatic process equal to P1 V1 minus P2 V2 by gamma minus 1. Let me write that value here. It is equal to P1 V1 minus P2 V2 divided by gamma minus 1 plus this quantity P1 V1 minus P2 V2. Okay, let us write P1 V1 minus P2 V2 outside 1 by gamma minus 1 plus 1. Simplify this value, simplify that value for getting gamma by gamma minus 1 into P1 V1 minus P2 V2. Gamma by gamma minus 1, you know, PV equal to RT, ideal gas equation. PV equal to RT for ideal gas. Then P1 V1 I can write as RT1 minus RT2. R is written outside. This R by gamma minus 1 equal to CV. R by gamma minus 1 equal to CV. CV equal to R by gamma minus 1. Then this steady flow reverse adiabatic work equal to CV gamma CV into T1 minus T2. You know, Cp equal to or Cp by Cv equal to gamma, from the Cp equal to gamma Cv. So in the place of gamma Cv you can write the Cp T1 minus T2, can also be written as Cp T1 equal to H1 minus H2. So from this the conclusion is steady flow reversible adiabatic work, steady flow reversible adiabatic work, reversible, should be very careful, steady flow reversible adiabatic work always equal to change in enthalpy of the working material. That is what it is given as option A. Steady flow reversible adiabatic work is equal to change in enthalpy when velocity change is negligible, elevation change is negligible. Option A is absolutely correct. Look at the B. Thermal power plants can be constructed to reject the heat at constant temperature. Absolutely correct. You know, in the thermal power plant, heat is rejected to the coolant available in the condenser. It can be practically possible to maintain the constant temperature during the heat rejection process for thermal power plant. That means the entire heat can be rejected at constant temperature without any practical difficulty for the thermal power. That is the beauty of the thermal power plant or Rankine cycle. The total heat can be rejected constant. It is like this. If you look at the TS diagram, temperature versus entropy diagram for thermal power plant, the saturation dome Look at the saturation dome. This is the saturation dome. Thermal power plant is working on Rankine cycle. Rankine cycle is having two constant pressure process, P1 equal to boiler pressure and P2 equal to condenser pressure. P2 equal to condenser pressure. Generally, you are allowing the superheated steam to the turbine. This may be the state where the steam is entering to turbine. That steam is expanding ideally or isentropically in the turbine, 1 to 2 isentropic expansion. Though you are allowing the superheated steam to the turbine, because of the expansion, the superheated steam may become wet steam. Though the superheated steam may become wet steam, under any circumstances, the drainage fraction at state 2 must be more than or equal to 0.9. That means, under any circumstances, moisture content at the exit of the turbine should not be more than 10%, right? Anyhow, this wet steam is entering to condenser where complete condensation is happening at constant pressure and constant temperature. That means these are condensation process. That means that is the heat rejection process for thermal power plant. In the entire heat rejection process, it can be possible to maintain the constant temperature. That is what it is given as option B. Thermal power plant can be constructed to reject the heat at constant temperature. Absolutely correct. B also absolutely correct. Look at the C. Centrifugal compressor, positive displacement compressors. No. Centrifugal compressors are dynamic compressors where the pressure is increasing by transfer of energy from high speed blade surface to gas particles. Whereas in our reciprocating compressor, the pressure increases by reduction in the volume of the material. That kind of compressor, the compressor in which the pressure is increasing by either reducing the volume of the material or by the backflow of the receiver gas, is coming under a positive displacement compressor. In the Roots blower, pressure is increasing by backflow of the receiver gas. That point clearly we discussed in the classroom. So, Roots blower is coming under positive displacement compressor. Similarly, reciprocating compressor also. But the axial flow compressor, centrifugal compressor, both are non-positive displacement compressors. They are technically called as dynamic compressors, where the pressure is increasing by transfer of energy from high speed blade surface to gas particle. That's why option C not correct. Centrifugal compressors are positive. No, not positive, non-positive. C not correct. C absolutely wrong. Next, D. Entropy change in the liquid is not the least. Entropy change in the liquid is not the least. Absolutely correct. You know, if you look at the entropy for different materials, entropy maintained by the solid is very less compared to entropy maintained by the liquid, less compared to entropy maintained by the gas. So, this is the entropy relation for different materials. Solid is maintaining the least entropy, liquid is not maintaining the least entropy. That is what it is given. Entropy change in the liquid is not the least. Entropy change is the least for solids only. That is why it is correct. That is entropy change in the liquid is not really correct. D correct. Means that option, that statement is correct. A, B, D correct. Only C option is wrong. Are you following clearly? Yes. Then let us take the another question. Look at this one. It is asking like this. Which of the following statements is / or correct? Look at the A. Latent heat of sublimation. Sublimation is the direct phase change process from solid to vapor. The sublimation and desublimation. Desublimation is the reverse process, opposite process of the sublimation. The direct phase change process from solid to vapor without having the intermediate phase called liquid called sublimation. Desublimation, the direct phase change from vapor to solid is called desublimation, is also called sublimation. Dear friends, remember, both sublimation and desublimation both are happening or both are occurring below triple point pressure. Okay. Anyhow, latent heat of sublimation is equal to sum of the latent heat of melting and latent heat of vaporization. Absolutely correct. Because sublimation is the combined process of melting and evaporation. That is why latent heat HFG for sublimation is equal to HFG of the melting plus HFG of the latent heat, generally marked by HFG vaporization. That is why this HFG of the sublimation is more than HFG of the vaporization or HFG of the melting process. Anyhow, this statement is absolutely correct. Look at the B. For all working substances, the melting curve slope is negative. No, the melting curve slope is negative for those materials which are decreasing their volume during the melting process. Best example is water. By the time the ice is melting, its volume is decreasing. So, if you look at the melting curve, for the water and other substances, let us take the pressure versus temperature. You know, there are three curves which are meeting only at triple point state. This is the what A to B is the sublimation curve, B to C is the vaporization curve, and B to D is the melting curve for water. B to D dash is the melting curve for those materials which are increasing their volume during the melting process. Anyhow, BD dash is the melting curve for the material which are increasing their volume during the melting. BD also melting curve for those materials which are decreasing their volume during the melting process. This curve is maintaining negative slope and this curve is maintaining positive slope, but both are coming under the melting curves only. This curve is maintaining negative slope means as the pressure increases, melting temperature decreases for those materials which are decreasing their volume during the melting process, right? Whereas the BD dash is maintaining positive slope for that kind of the material which are increasing their volume during the melting process, right? Melting process can maintain the positive slope during the melting process. That means by the time the pressure increases, melting temperature increases. Anyhow, for all the materials, melting curve slope is not negative, but what it is given, look at the B. For all working substances, the melting curve slope is negative. No, not correct. B is absolutely wrong. Next, 1 Kelvin is equal to 1 by 273.16 times the triple point temperature of ammonia. No, wrong. C is wrong. You know, triple point temperature of water, triple point temperature of water that is H2O equal to, right, thermometer temperature which is in degree centigrade at triple point state plus 273.15. It is equal to triple point temperature is 0.01 plus 273.15. 15. That is 15. It is equal to 273.16 Kelvin. Therefore, 1 Kelvin is equivalent to 1 by 273.16. Right, 1 Kelvin equal to 1 by 273.16 times the triple point temperature of water. not ammonia, water. That is the Kelvin definition. 1 Kelvin is equivalent to 1 by 273.16 times the triple point temperature of water. But what is given? 1 Kelvin is equal to 1 by 273.16 times the triple point temperature of ammonia. Not correct. If it is water, that is correct. Look at the D. PdV not equal to 0 for free expansion process. Absolutely correct. For free expansion process, the flow of working fluid from high pressure compartment to low pressure compartment, or from high pressure compartment to perfectly evacuated compartment is called free expansion process. Free expansion process is irreversible process. Free expansion process is the irreversible process or irreversible closed system process, like how the throttling process is the irreversible process for any steady fluid base. That means throttling process is the irreversible steady flow process, whereas free expansion process is the non-flow irreversible process. Anyhow, since the free expansion process is the irreversible process, irreversible process, you cannot use the work formula equal to PdV. The work equal to PdV, only, this is the non-flow work, only when the process is happening reversibly. This formula you cannot use for the free expansion process, because free expansion process is coming under irreversible process. Okay. Now, for the free expansion process, pressure is not 0, dV not equal to 0. Though the pressure is not equal to 0, dV is not equal to 0, by simply taking or by simply substituting these values, you cannot decide, the non-flow work is not 0 for the free expansion process, because in the free expansion process, no mechanical part is moved by the gas flow. The free expansion process is like this. The flow of the gas, it is like this. Let us take a container. This container is divided into two parts. This is the compartment 1, this is the compartment 2. In the compartment 1 side, assume some high pressure gas is there. And compartment 2, second compartment is perfectly evacuated region. It is the evacuated region. And this part is called barrier. Once that barrier is ruptured, what is happening? This high pressure gas is rushed towards the evacuated region. That means the gas particles are freely flowing from high pressure compartment to evacuate region. That kind of process is called free expansion process. Now, free expansion process is highly irreversible process. Right? For this process, pressure is not becoming 0, dV also not becoming 0. Though the pressure and dV not becoming 0, the PdV equal to 0. No, sir, PdV, right? PdV not equal to 0. PdV not equal to 0. Though the PdV not equal to 0, thermodynamic work is 0. Thermodynamic work 0, because thermodynamic work sense is that a kind of energy causing for lifting the load or carrying the load is called thermodynamic work. A kind of energy which is causing for lifting the load or carrying the load is called thermodynamic work. By the time the gas particles are freely flowing from high pressure compartment to evacuated region or low compartment region, no mechanical part is moved by the gas flow. That's why thermodynamic work is 0. Though thermodynamic work is 0, PdV not equal to 0 for free expansion process. That's why it is given as D. Look at the D. PdV is not equal to 0 for free expansion process. Absolutely correct. So here A correct, D correct, B and C absolutely wrong, right? So D also correct. Dear students, our time, scheduled time is 1 hour. I tried to explain as many as problems, right? The remaining problems, remaining questions we will discuss in the second part of thermal, that is under applied thermodynamics, on 30th of this month. Okay, I hope all of you clearly understood or not. Thank you. All the best. God bless you.